Hey y'all, today is March 17th, St. Patrick's Day, and we are talking about theoretical versus experimental probability. Let's get started. So first off, some definitions. Theoretical probability is what should happen in an experiment. So for example, if we are tossing a coin, the probability of it landing on heads is 1 out of 2. We write that as 1/2 because there's only two sides to a coin. There's heads or tails, right? So the probability of it landing on heads is 1/2. Okay. Now, experimental probability is what actually happens in an experiment. So, for example, if a coin was tossed 100 times, heads appeared 60 times. Therefore, the probability of the coin landing on heads in the next toss is, well, I'm going to say 60 over 100. Now, that's a fraction I can reduce. I can start first by just taking those zeros off. So I get 6 out of 10, and I can still reduce that fraction. 2 goes into both of those numbers. So 6 divided by 2 is 3. And 10 divided by 2 is 5. I can't reduce that any further, so the probability of the next toss landing on heads is 3/5. Okay? So notice experimental and theoretical probability don't always match. And that's okay. They don't have to match. Okay. So now that we've talked about what theoretical and experimental probability are, let's get started with some examples. So the example that we have here tells us that we need to roll a standard die 60 times and record the results in the table below. Now, I don't have a dice that I can do that with, so I'm going to go to a website, and we're going to do this from a website. So here I am. We've got a standard 6-sided dice, and we're going to change it so that we roll it 60 times because it tells us to roll it 60 times. Okay, so now I'm going to hit go, and it has rolled it 60 times right here. I've got 60 different numbers. Okay, now I'm going to hit show stats, and I have this right here. I see that 1, I had 10 times, 2, I had 15 times, 3, 13 times, and so on. I'm actually going to take a little screenshot of that so that I can include that in my notes, and that will just help me out. So we're going to say done, save to photos. And now I'm going to go back to my notes, and I'm going to insert that image right here, make it a little bit smaller, right there. Okay, so we're going to record those same results in our table that it's given us here. So we got 1, how many times? Well, it tells us 10 times, 2, 15 times, 3, 13 times, 4, 8 times, 5, 8 times, and 6, we had 6 times. So if I were to add all of these numbers up, it should be 60. And just because I used a website and didn't actually roll the dice 60 times, I'm going to double check. So 10 plus 15 plus 13 plus 8 plus 8 plus 6 is indeed 60. So the website worked great for us. So now we're going to answer each question based on the theoretical probability and experimental probability using our results, so using our table here. So number 1, what is the probability that the next roll is an odd number? Okay, so first of all, theoretical probability. How many odd numbers are on a 6-sided dice? Well, the odd numbers are 1, 3, and 5. So 3 of the 6 numbers are odd, right? So theoretically, 3 of 6 are odd. What does that reduce to? Well, that reduces to 1/2. Now, a lot of times when I'm comparing theoretical to experimental probability, I like to compare the percentage. So I often do convert this fraction to a decimal or to a percent. The way to convert it to a decimal is just you can put 3 divided by 6 into your calculator and you get 0.5. So like I said, I just like to have that just so I can compare, because sometimes when my denominators are different, it's hard to compare my fractions. So I know that that is 0.5, okay? So now let's look at the experimental probability that the next roll is an odd number. So again, we're still looking at 1, 3, and 5, but 1 occurred 10 times, 3 occurred 13 times, and 5 occurred 8 times. So I'm going to add 10 plus 13 plus 8. So 10 plus 13 plus 8. When I add that together, I get 31. So 31. Now, 31 out of how many rolls did we do on that website? 60. 31 out of 60. Now, I can't reduce that. So I'm just going to go ahead and convert that to a decimal. So 31 divided by 60 in my calculator. And I get a repeating decimal, but I get 0.516 repeating. Okay, so keep in mind this other one over here was 0.50. So now I have 0.516 repeating. Okay, so which one is bigger? Well, this one is bigger. So the experimental probability is greater than I expected it to be. It's more than I expected it to be. Okay, let's look next at number 2. So in number 2, what is the probability that the next roll is a 1 or a 4? Well, on a standard 6-sided die, 1 happens one time and 4 happens one time. So that's just 2 out of 6 total outcomes. Well, what does that reduce to? That reduces to 1/3, right? So that is my theoretical probability. It's what should happen. Now, 1/3 as a decimal, 1 divided by 3 is 0.3 repeating. So I'm just going to write that, 0.3 repeating. Okay, so now let's look at the experimental probability. What's the experimental probability that the next roll is a 1 or a 4? Well, 1 and 4, 1 occurred 10 times and 4 occurred 8 times. So 10 plus 8, I'm going to add that together. 10 plus 8 is 18. So 18 out of 60 rolls that we generated on that website, right? Now I can reduce this. I know 3 goes into both of these numbers. 3 goes into 18 6 times, and 3 goes into 60 20 times. Now I notice that I've got 2 even numbers, so I can reduce this even further. So because they're both even numbers, 2 goes into both. 6 divided by 2 is 3, and 20 divided by 2 is 10. So I get 3/10, which I know if I put 3 divided by 10 into my calculator, I get 0.3. So 0.3. So keep in mind that 0.30. So when I compare my 2 decimals, I can tell that this one is actually smaller than I expected it to be. Okay? Now let's look at number 3. So what is the probability of the next roll, or that the next roll is at least 2? That means 2 and bigger, right? So 2 and bigger means I'm talking about 2, 3, 4, 5, and 6. So that's 5 of the 6 numbers. So 5, oops, let's change that color. 5 of the 6 numbers. Well, I can't reduce that fraction, so that just is my probability. But like I said, I like to convert everything to either a decimal or percent. It just helps me compare them. So 5 divided by 6, when I put that into my calculator, I get 0.83 repeating. So 0.8 doesn't repeat, but 3 does. Okay? Now, let's compare that to the experimental probability. So, what is the probability that the next roll is at least 2? Like we said earlier, that means I'm looking at 2, 3, 4, 5, and 6. So everything but the 1, right? So I know that if I rolled the dice 60 times and it landed on 1 10 times, I can just subtract. 60 minus 10 is 50. And I would get that same number if I had just added up 15 plus 13 plus 8 plus 8 plus 6. I'd still get 50. So I have 50 out of 60. Well, does that reduce? It sure does. I can take off those zeros. So I actually do get 5 over 6. So in this case, my fraction is exactly the same. So that means my decimal is exactly the same, 0.8 with a 3 repeating. So in this case, my theoretical and my experimental probability match. So that's not always the case, but sometimes that does happen. Sometimes it does match. Okay, let's look at the next one, number 4. Out of 100 rolls, about how many times would you expect to roll a 3? Okay, so we're actually going to predict how many times we would expect to roll a 3 if we were to roll the dice 100 times. So, how many times does 3 occur on a 6-sided die? Just once. So, that is 1 out of 6, right? So, I'm going to take that and I'm going to multiply that times 100. And I'm multiplying it times 100 because it tells me out of 100 rolls. So, 1 divided by 6 times 100. When I put that into my calculator, I'm going to type it just like that, 1 divided by 6 times 100. And I get 16.6 repeating. So 16.6 repeating. Now, here's the thing. I can't have a decimal because how many times would I expect to roll a 3? You can't have partial times, partial turns, right? So we're actually going to round, and we're going to round based on whatever our decimal is. So because I have a number bigger than 5 here, I'm going to round up. So I would expect about 17 times to roll a 3. Okay? So based on the theoretical probability, I would expect to roll a 3 about 17 times. And I use this little squiggly equal sign because that means about. Okay, it just shows you that I estimated that. Okay, now let's look at the experimental probability to predict. So out of 100 rolls, about how many times would you expect to roll a 3? Well, here's the deal. We rolled a 3 13 times out of 60. So I'm going to start with that probability, 13 over 60. Can I reduce that? Nope, I can't. So I'm just going to then multiply that times 100. So the way I'm going to type this into my calculator is 13 divided by 60. So let me start over. Sorry, y'all. 13 divided by 60 times 100. And I'm going to see what I get into my calculator. So 13 divided by 60 times 100. And I get 21.6 repeating. So we have 21.6 repeating. Okay, now, like I said before, I can't have a partial roll, right? So I can't have a 0.6. And because that is a 6 and it's a bigger number, it's bigger than 5, I'm going to round up. So about how many times based on the experiment would I expect to roll a 3? I'm going to round this up to say about 22 times. Okay. So now, number 5, do the theoretical results match the experimental results? So I'm going to say no. Some were higher than expected. And some were lower than expected. So the reason I say that, remember, we first compared in number 1 these two decimals, and we said that this one right here was higher. So the experimental probability was higher than we expected it to be. And then in number 2, we compared these two decimals. And we said that this one right here, the 0.30, is lower than what we expected it to be. Okay? Now, oddly enough, in number 3, we got the exact same probability, so those matched. But that's not always going to happen. Okay? So now, number 6, how could the experimental results get closer to the theoretical results? Well, the way to get the experimental and the theoretical results closer is to do more trials, or in this case, more rolls. So the more trials or rolls, the closer the experimental probability will be to the theoretical. Okay, let's move on to page 12. So we're just doing some more examples here. So a letter in the word Excel is chosen 50 times. Results are shown in the table below. So A, what is the theoretical probability of choosing a C? Well, when I look at the word Excel right here, C happens 2 times. 2 out of 1, 2, 3, 4, 5. Okay? So 2 out of 5 times. I can't reduce that fraction, so that is my probability as a fraction in simplest form. But like I said, I like to convert it to either a decimal or a percent. So 2 divided by 5, when I put that in my calculator, I get 0.4. 0.4. Now B, what is the experimental probability of choosing a C? Compare this to the theoretical probability. Well, based on this experiment, so I'm looking more at the frequency side here. C was chosen 5 times once and 7 times for the second C. So 5 plus 7 is 12. So it was chosen 12 times, and how many times were we choosing letters? Well, it tells us right here 50 times. So 12 out of 50. So 12 divided by 50, I can reduce that. So 2 goes into both of those. 2 goes into 12 6 times. 2 goes into 50 25 times. So 6 over 25. I can't reduce that any further, but I can convert that to a decimal so I can compare. So 6 divided by 25 is 0.24. So 0.24. So now I'm comparing these two decimals. Which one is bigger? Which one is smaller? Well, this experimental probability is smaller. So the experimental probability is lower than expected. The experimental probability is lower than expected. Okay, let's move on to number 8. So in number 8, it says the spinner to the left is spun 80 times. Results are shown in the table below. So we've got our results. What is the theoretical probability of the spinner not landing on polka dots? So that means it could land on stripes or solid, right? So now, of the 3 options, it's not landing on polka dots. So that leaves me with 2 of the 3 options, right? So 2 out of 3. That fraction is in simplest form, so I can't reduce it any further. Oh, but actually, I wasn't looking at the right thing. I needed to look at the spinner, didn't I? Because the spinner over here has more than just 3 sections. So let's look at anything but polka dots. So I cannot include this section here, and I cannot include this section here, but I can include all the other sections. So 1, 2, 3, 4, 5, 6. 6 out of 8 sections, right? So 6 out of 8 sections would be not landing on polka dots. Well, what does that reduce to? Well, 2 goes into 6 3 times, and 2 goes into 8 4 times. So 3/4. Okay? Well, 3 divided by 4, if I put that into my calculator, I do get 0.75. And the only reason I'm doing that is so that I can compare more easily because my fractions might have different denominators. Okay, so B, what is the experimental probability of the spinner not landing on polka dots? Compare this to the theoretical probability. So, not landing on polka dots means it lands on stripes 27 times and solids 35 times. So, I can add those together, or I can take the number of times the spinner was spun, 80 times, and I can subtract the number of times it did land on the polka dots, which was 18 times. So 80 minus 18, when I put that into my calculator, I get 62. So 62 out of 80, right? Does that reduce? Well, I know 2 goes into both of those. So 2 goes into 62 31 times, and 2 goes into 80 40 times. I can't reduce that any further, so that right there is my fraction. But what is that as a decimal? So 31 divided by 40 is 0.775. So 0.775. So they're pretty close, but when I compare the hundredths place value, 5 to 7, I see that this one here is bigger. So that means that that probability is higher than expected. So higher than expected. Okay, now let's use samples to predict. So number 9, a day of the week is chosen at random 40 times. Results are shown in the table below. So theoretically, if a day of the week is chosen 150 times, how many times would you expect that day, or expect a day that starts with the letter T? So let's just consider the days of the week right here. How many start with the letter T? Tuesday and Thursday. They're the only 2, right? So that's 2 out of 7 days. So 2 out of 7 days. But we're told that if we choose it 150 times, how many times would we expect that? So I'm going to take 2 divided by 7 and multiply that times 150. So the way I put that into my calculator is 2 divided by 7 times 150. And I'm going to see what I get. Okay, so 2 divided by 7 times 150. And when I put that into my calculator, I get a long decimal. Looks like it doesn't end. So I've got 42.85, and it keeps on going, right? So because we can't select it, or we can't have it happen a point something of a turn, we've got to round that. So let's round that to a whole number. Well, because I've got an 8, I'm going to round that up. So I'm actually going to say about 43 times. So about 43 times. Remember that little squiggly equal sign means about. Okay, so now we're going to consider the experiment. So based on the experiment, if a day of the week is chosen 150 times, how many times would you expect a day that starts with the letter T? So we're considering our Tuesday and our Thursday. So Tuesday was selected 2 times, Thursday was selected 8 times. That's 10 out of 40 times. So 10 out of 40. Well, what does that reduce to? That I know reduces to 1/4. Okay, now if it's chosen 150 times, so I'm going to multiply that times 150, and that's how we're going to predict. So we've got 1 divided by 4 times 150. And when I put that into my calculator, I get 37.5. Now again, we don't want a decimal, and because I've got a 0.5, I'm going to round up. So I'm going to say about 38 times. Now, one thing I want to point out when you're using these results to predict, you don't always have to reduce your fractions. So I could have typed into my calculator 10 divided by 40 times 150, and I would have gotten the exact same answer. So if you want to try that real fast, 10 divided by 40 times 150, you still get the exact same answer. So 10 divided by 40 times 150 is still 37.5. So sometimes it's easier not to reduce your fraction, to skip that step and just go straight to multiplying. It works the same way. Okay, let's look at number 10. A small deck of cards has 4 kings, 3 queens, 2 jacks, and 1 ace. Eli chooses 1 card at random 75 times and records his results in the table below. Theoretically, how many times would you expect to draw an ace out of 200 draws? Okay, so we're talking about drawing an ace, right? So here's what I know. He's got 4 kings, 3 queens, that's 7, 2 jacks, that's 9, and 1 ace. So that's 10 cards, right? So how many of them are aces? Well, there's just 1 ace. So 1 out of 10 cards. I don't need to bother reducing that. It doesn't reduce anyway, but I'm going to multiply that with the number of draws that we're going to maybe make. So 200. So the way I put this into my calculator is 1 divided by 10 times 200. So 1 divided by 10 times 200 is 20. So I get 20. So 20 times. This time I don't have to round, which is really nice. Okay, and then B, based on the experiment, how many times would you expect to draw an ace out of 200 draws? Well, in our experiment here, he drew an ace 12 times. 12 times out of 75 times, right? So 12 out of 75. Now, that fraction does reduce, but like I said, you don't always have to reduce these because we're still predicting. So we're going to multiply that times 200. So the way I put that into my calculator is 12 divided by 75 times 200. So 12 divided by 75 times 200. And I get 32. So 32 times. So that is the end of our notes on theoretical and experimental probability.